Okay. So, good evening everyone. It's still hot outside. Today we're going to talk about integration and processing of data in an organization. And it isn't that often that you can come into an organization and basically have a green field to start from. Basically, most of the times there already is some sort of technology stack available that you have to deal with, cope with. So, what will we be doing today? We will start on what would you do if you come in an organization and there is nothing. There is no stack available. How would you deal with that? The second step is that we're going to look into the building blocks. What are these common components that you see coming back in every single data setup that we talk about? I also want to put some focus on the team itself, because there are some things that you need to know about them. There are certain roles in there and they not always play well together. At some point in the future, you will get to the point where you actually want to start building your stuff. And I often get a question like, how do we do that? I mean, yeah, we have a plan, but how do we start? How do we start building new things? And once you come in an environment where they are already having some of these components, how can I contribute to them? How can I make new cases or implement new cases? I'll also give you a small example of an architecture. Like one of the ways how we integrate data system back into the organization, real time as well as batch. And the last part, again, is some advice, things you have to, or you can remember, or forget, whatever. But those are things that I learned, and I hope to give them to you so you don't make the same mistakes as I did. You already knew who I am, so we don't need to go through that again. So let's see what happens when you start from scratch. You have you get to a client and they have nothing. The best thing that they have is just a database in which they store their data, but that's it. So what do? Well, you start by defining a vision. And this is an important part when you're starting from scratch, because if you go to an organization that already is dealing with big data or dealing with data as a whole, they will already have a vision. They will already have a way of working and know what they want to do with their data. Well, hopefully they do. If they don't, make yourself ready for a nice conversation. So, a vision is much more about values and actually putting technologies in place. It's about what are we going to do? What is important in the data system? How are we going to approach this? And what kind of role is data going to play inside our organization? Do we just want to use it for reporting and have humans make the decision? Or do we want to automate and make the data drive the processes themselves? You will always have to do some trade-offs. Real-time versus batch, for example. Or data-driven versus human-driven. These are things that come back every single time again. So let's see about a few of these visions that I came across. Like the first one was a statement from one of the companies I worked with. And they said, like, we want to be close to our clients. We want to provide better services by giving them insights into how we do things. They want to open up to their clients and actually give them inside information. Well, this organization had quite a few clients. This is not some simple feature that they were just thinking about. If you have 100,000 and more clients, it means that you need to design your systems in a different way. At that point, you're starting to reach internet scale, which means that at any moment in time, you can have 1,000 users looking at your data So you need to build a system that can cope with that. The second one was something totally different. This was more like a traditional company that was very conservative when it came to data, and they mainly focused on human interaction. So they didn't want much automation in a way that they dealt with data. They just wanted to be an indicator and to guide them into making decisions. I'm not saying that you should make your data make the decisions themselves. Make sure that there is always a human to press the red button, especially if you're dealing with rockets. But when you look at automation, there is something to say about it. So, once you have more or less of a vision on how you are going to tackle data and how you're going to integrate data into your organization, you understand what is important about your data. Then we go to the next step. We need to understand the building blocks that we have, because we are going to build the biggest Lego sculpture that we can. But in order to do so, we need to know which bricks we can use. And the first brick, obviously, is data storage. We need to be able to store data, and preferably in a fault-tolerant way, and even much more important, in a scalable way. Because we cannot know what will happen in 2 years from now. But what we don't want to have is that at that point we have to say like, meh, we need to build a new or a total new system or a total new architecture. So when you look at a data system, there are some characteristics that you have to take into account. Like there are real-time data storage systems. If you look at Kafka, for example, you can use Kafka to store data. There are batch systems. Look at HDFS, look at S3 or Glacier. These are systems much more interesting when you have a large amount of data. I get files in, every file is 1 gigabyte, and I get a file in every day, something like that. You will probably store that on HDFS. If you have IoT sensors and you are getting in these events from these IoT sensors at a continuous rate, then you will probably look at a real-time solution like Kafka. We talked last time about read-optimized versus write-optimized. Of course, this has an impact as well. You will see that in a bigger architecture, you will not have only one data store. As we said last time, you will have several of them. So you need to understand which ones you are going to optimize for what. Some of them you're going to optimize for reading, others you're going to optimize for writing. A few of the examples when you talk about data stores or data storage, I tried to list a few of them. There are millions of them. But some better known are HDFS, Hadoop Distributed File System, S3, Kafka. Kafka is more known as being a streaming platform. Some people like to say it's a message broker, but it's actually much more than that. But at the core, Kafka is built as a database. NAS or SAN, network attached storage. Blockchain is also a way of storing data. It's a ledger, distributed ledger, high latency, yeah. But it is a way of storing data. IPFS is something that's built on top of some of these ideas. Elasticsearch, Redis, the more traditional databases, it doesn't really matter. All of these are ways to store data in an efficient way. Well, having or storing your data is only part of the solution, of course. You can store as much data as you like, but at some point you want to do something with that data. You want to transform it, or you want to convert data into information, like we used to say, or data into insights. And for doing that, we need processing frameworks. We need a way to process our data, to get the data from one file or several files and make or transform it into something that we can do something with. Something that has value. And please, not only a report. So, when you look at processing frameworks, you basically have the same kind of questions that you have to ask yourself. Are we going for real time? Are we going for batch? That's the obvious one. There are some technologies that can do both. For example, Flink. Flink is a technology. It's pretty cool. They have a pink squirrel as a logo, which already says enough. But they are able to do batch and real time within the same technology platform. Be careful, that doesn't mean that I can write one application and it can handle and it can work in batch as well as in real time. That's not the case. But you can use Flink and you can build an application for real time and an application for batch. That sounds a bit silly, but back in the day, when we were starting with big data, we had different languages, even different programming languages that we would use to do real-time versus batch, which was a big hazard, or it really was quite complex, because you needed to write your logic twice, once from an incremental point of view, and the other from a full point of view. Because if you do streaming, you don't have all the data, because the data is continuously coming in. So if you want to do a count, or you want to do a sort, that's one that still has to be solved. Maybe with quantum computing that will solve something, but right now we can't. So what we do is we start to window, we start to take messages together in units that we can deal with. And then we can sort within that unit. So Flink allows us to do real-time processing as well as batch processing. Kafka Streams is especially for Kafka. This is real-time processing only. Apache Beam, I think, can do both as well. Pulsar, Spark Streaming, Spark. So Spark, who has heard of Spark here? Nobody. Cool. Spark became very, very famous and very popular right now. Because back in the day, we started with MapReduce. And MapReduce was basically, you only have two operations. You have a map and you have a reduce. Basically, I do a transformation or I do a group by. That's basically a translation of it, or an aggregation. And it really felt like programming assembler. Who knows what assembler is? Programming language? Well, language. It's a thing that computers talk. It's the lowest level of programming language that you can use to interact with a computer. So MapReduce for us was the lowest level of programming language we could use to talk with data or to work with data. But it was very tedious to work with. So then Pig came along, and Pig offered us a new language to work with data. Their language was called Pig Latin. And they made it easy to basically write these SQL-like statements to process and to transform your data. But then all of a sudden, Spark came along. And what Spark did different is that they took a lot of the data in memory, which meant that things were going a lot faster than before. With MapReduce, the only thing that we could do was basically read it from one file in your file system, do some processing, and write it to the next. But with Spark, we had the ability to load things in memory and to reuse it in different steps of our pipeline. Now, Spark became an ecosystem by itself. With Spark, Spark Streaming, there are other ones as well, Spark SQL, for example. All of these basically are built on top of what is known as Spark. So when you look at processing frameworks, especially in batch, make sure that you have a look at Spark. It's like the de facto standard right now. Spark Streaming, you have to be careful with, because they do micro-batching, there is going to come an update where they will not do micro-batching anymore. So micro-batching basically means that they take together a set of events that come in and then let you work on that set of events, which is different from Kafka, where, for example, and Flink, where every event is treated by itself. So Spark certainly want to take into account. So what Spark, I get the impression that Kafka right now is becoming the same thing as Spark in real time as Spark is in batch. So using Spark and Kafka, it somewhat makes sense actually. But yeah, you want to process your data, but you don't have the data on your platform yet. Because you have this organization and they have relational databases, operational databases, which they really, really do not want you to play with. But you need to have that data in order to do something. So you need to have a way to pull data out of these systems and into your data platform, onto your data storage system. So you can use these processing languages to basically transform the data and transform it from data into insights. So some of the technologies that we use for doing that, for pulling data out of existing systems in the organization, is Flume. Flume is pretty good in getting files out. So if you have a mainframe that is every night generating CSV files, use Flume to get them and to import them on your data system or in your data store. Scoop is meant for everything SQL related. So if you need to get information from a database, a relational database, you can use Scoop for that. You can describe the query that he needs to run every night, and Scoop will make sure that that data is pulled out, transformed into something that can be stored on a distributed system or on your storage system. When you look at real time, you need to do things different. Because when you're dealing with real time, as I said, you deal with every event individually. Like if you work on large data sets, take any data file, most of these data files, take a CSV file. Who knows what a CSV file is, or who doesn't know? Maybe that's a different question to ask. So CSV files, basically every line in the file is a record. And CSV files became very hip again the moment that we started working with big data, because they're so easy to work with. But the thing is, if you have a 1 terabyte CSV file, right, you cannot take that and run it through your processing line. You need to do things differently. You need to go through these records and process them. What is different with Spark and batch technologies is that they're going to take a subset and work on that subset and do the processing on that. What is different in real-time technologies is that they are going to read the whole file line by line, transforming each line into an event, and then processing the event through your pipeline, joining it again, and having streams of data that come together and go apart again. So if you want to do that, you need different technologies than Flume and Scoop. You need to have something like Kafka Connect, which allows you to connect external systems with your internal data system or data platform. Not only for getting data in, but later on, once we have generated the insights, we can basically push it back into our organization as well. And we can use Kafka Connect for that as well. There is Spark SQL, which allows you to make a connection to SQL databases as well as to other NoSQL databases. Like for example, with Spark SQL, you can actually go to Elasticsearch and get information out. Have a look at these technologies, or just keep them in your mind the moment that you have to integrate your data platform into your organization. So we saw ways of integrating data. We saw that we were going to process data, and we saw that we are going to store data. But we don't want to have a human sitting there every night saying like, okay, now you have to launch a job. Now you have to launch a job. It's like the worst job ever, right? We want to have an automated system that does that for us. Much more, as I told you last time, it could very well be that you have one job that generates data that is being used by a second job that also generates data. So you can have a whole cascade of multiple jobs to accomplish one end goal. And in order to make that work, in order to get your grip on that, and in order to scale that schedule that on the right moment, you need a scheduler. And you have few available right now. I think Airflow is one of the most popular, especially for the people who are using Spark, because it integrates very, very well. And you can actually see what kind of data was generated when. So it gives you a lot of feedback. Because one of the hardest things to do is debug a job that goes wrong on a distributed system. Because the information that you need is shattered out of your whole big data environment. There are tools right now that try to get that together, but still, it's tedious to do. Uzi is one of the more older schedulers. It became particularly popular with the whole Cloudera distribution. But in all honesty, I think most organizations have moved towards Airflow, especially if they are doing something with Spark. I put Jenkins in here, and Jenkins is, for people who know about Jenkins, Jenkins is actually a build server. It's a build server for building Java applications or other applications. But I have seen Jenkins being used a lot of times as something to trigger your jobs, something to schedule your jobs, because it's so easy and so easy to integrate with it. It has a very nice API and you can embed it in your applications, which is basically what you want. So choose your poison, basically. What is important with schedulers is that you can trust them. So you know that when the job is being executed, for example, it waits for the job to finish and then launch the next job. This seems quite obvious, but some of these technologies don't even have those basic meaning, or you have to build that yourself or configure that yourself in these technologies. So make sure that you look at a few of those before you make a decision on which one you're going to take, which is basically true for all of these building blocks. Something that became quite popular. So when I started with big data, we only had big data, which meant that if we wanted to know something, we had to run a job, and the job could take quite an amount of time to complete. But then all of a sudden, Cloudera released Impala. And Impala was different. Impala allowed us to make SQL queries and do ad hoc querying on top of our data. Yeah, sure, we had Hive, but Hive translated into MapReduce jobs. These MapReduce jobs could run for a few days before you got a result out of it. But now with Impala, we basically have the power to do ad hoc queries, or at least do them a lot faster than we were used to. Now, Impala was a bit like the thing that happened on the Cloudera side. Obviously, there are two big distributions in big data, which was Cloudera and Hortonworks. Now there is only one big distribution in big data, which is called Cloudera Hortonworks. So they merged together. But back in the day, there was quite some competition. And while Cloudera had Impala, you saw that other people were looking into other ways of doing things. Hortonworks, for example, they wanted to optimize Hive. They wanted to make Hive faster. So what they did is they removed the whole MapReduce stuff underneath Hive, and they basically said like, let's use Des, which is a different kind of schedule that they used. And things went faster as well. Then you had Mapper. Mapper is another distribution, and they started working on Drill. Needless to say that you have quite some choice when you want to do ad hoc querying today on large data sets. But keep in mind that usually you will still need to prepare your data in one way or the other. Like for example, if you want to use Kudu, which is more like the successor of Impala, you will need to prepare your data before you can actually work with it. The same is especially true for tools like Cubana, because Cubana works on Elasticsearch, which basically means that you need to format your data in such a way that you can store it in Elasticsearch and that it makes sense. If you just dump your data in Elasticsearch and try to do some querying on top of that data, it's not going to work. You will definitely run into issues with that. So ad hoc querying became important. I still consider it as something quite dangerous. Why? Because you give people the power to basically launch a query that will take down the whole system. In one of my first jobs, we had a friend of mine who basically put a debug statement and forgot to remove it. So every time he did an Impala query, he would log every record that he got, that was returned, which meant that we basically replicated our whole data store into our log files, which was quite a problem because we didn't anticipate it for that many logs. These things you need to watch out. Also, since this is clustered technology, it means that if you make a mistake and the cluster goes down, then your whole team is probably just sitting there waiting for the thing to get solved. It's going to cost you a shit ton of money. These days, it's very hard to put something as complex as a distributed system in production without having some sensible level of monitoring, which means that you can have insights into what is going on with your system. This is important in batch. It's way more important in real time, because you need to know if something goes wrong, where it is going wrong. And you will learn by doing basically how you should build systems to make that predictable, to make sure that if something fails, it fails in a predictable way. It sounds like magic, but through some good engineering practices, you can actually make that work. So monitoring systems, when you look at the distributions like Cloudera, for example, they have their own monitoring system built into their platform. If you do not want to use that, you can look at something called ElkStack, which is Elasticsearch, Logstash, and Cubana, which is a combination to basically do not only application logging, but also application performance monitoring, which basically means that you're going to look at your application and continuously monitor the throughput, the latency of requests that are being done, or of processing that's being done. So it gives you a lot more insight, not only on the technical level, but also on a functional level. What we try to do right now in all the projects that I'm working on, we try to build, for every application that we build, we have a monitoring dashboard, because we need to know what is going on. And that is a monitoring dashboard not only for the technical stuff, but mostly for the functional stuff. So reports became boring because they don't change unless you rerun your whole job. So we really, really like these dashboards. The ability to have a website or web application or a mobile application, or just putting a screen somewhere that will change the moment that new data becomes available, the moment that new insights become available. That's the thing that really triggers business, apparently. There are some good examples. Like with Cubana, you can actually do this kind of thing. Cubana allows you to basically write a query and drag and drop components that visualize data in charts, in numbers, in maps. Doesn't even matter. Tableau can do something similar, but Tableau is more, the places where I've seen Tableau being used are places where they usually use it on one desktop computer or multiple desktop computers. Not really as like a service offering that you give to the rest of the organization to play with. It's more for those selected few that are allowed to do reporting. You can always write your own. I would really suggest you not to do that because dashboarding is quite complex. But there are also free alternatives available. Well, Cubana obviously is free. But Mosaic and Freeboard are also technologies that you can use. You need to modify them a bit because that's, yeah, you get something for free. You have to work with it or work on it to make it work. So make sure that you take your time. If you want to do dashboards, do not make the mistake to think that people will look at dashboards. Right? There's nobody ever who's going to be proud to say, yeah, my job is to watch dashboards the whole day. You don't want that. Blah. I forgot one. What you basically want is you want to get a notification if something goes wrong. You want to be notified, hey, those sales figures are dropping massively. Take your time and go have a look. At that point, I want to have an environment where I can start searching what is going on. That is much more important than having that dashboard sitting there and presented on a screen when you enter your company. Nobody looks at that, not even for the weather. One other thing that's pretty important and that actually became pretty important, I think the last 2 years, especially since people started talking about GDPR, is the fact that you need something for doing data governance. Data governance means that you can keep track of not only the data that you have available, but also the processes that will do manipulations of that data, that will do transformations of that data. In the best possible scenario, you should be able to say like, okay, if somebody asks, this is what we're doing with the data from A to B. If somebody asks like, how could you ever make this prediction for me? You need to be able to say like, okay, we first take your data from there and there and there, we combine that with weather data, with traffic data, and in the end we come up with this. It's staggering how many organizations have no idea of all the processes that are in place that are basically manipulating data. If you would ask them, the best way to look is to look in the scheduler and see what is scheduled. But that doesn't give you insights into that. If I have a source data set, a file with personal data in there, then everything that is deducted from it might become or might contain personal data as well. I need to be able to see that lineage. I need to be able to see how data is being processed. How can you do without? So there is an alternative, or there is an initiative called Apache Atlas that tries to do that. That allows you to model your processes, that allows you to model what data sets you have. Streaming data sets, batch data sets, it doesn't really matter. It allows you to say like, these are my data sets, and these are the processes that will convert those data sets into other data sets. Cloudera Navigator is more the same. They are a bit more mature because they have a whole organization sitting behind them basically for writing it. Apache Atlas is open source, so anybody can use it if they want to. Of course, you have the more commercial platforms as well. So organizations who only deal with data governance. Here in Belgium, we have Calibra, who probably some people know of. You have Axon as well, who is especially, I have the impression that it's especially interesting or popular within banking environments. But yeah, pick your choice. If you go to an organization and they're working with data, chances are high that they either do not have a data governance solution or they have one that is insufficiently used. So with GDPR, a lot of people said like, oh, we need to govern our data, we need to be able to see what data is, and we need to have a place to basically put the rules on how to manipulate and obfuscate the data. Because all of a sudden, we needed to anonymize the data and we needed to encrypt data. And to know what data you needed to encrypt, they basically said like, use a metadata tool, like Axon for example, and put your rules in there. But data governance goes a lot further than that. Data governance is something that goes from the front to the end. Let's take a moment, if anyone has questions or wants to call bullshit, now is your time.
I wonder, why is there so many different building blocks and that no one yet is trying to have a solution that regroups, let's say, the schedulers with the integration frameworks, to have somebody kind of integrated because it's so everywhere?
That's a very good question. The thing is that when you buy a platform, a distribution, big data distribution, like Cloudera for example, what you get is this box with these building blocks in. But it's up to you to basically come with an architecture or to come with a way of using these building blocks and to make something that works. I used to have a slide in my presentations of a Ferrari, because usually that's the thing that people think that they're buying when you buy a distribution. But in fact, you get all the parts to build yourself a Ferrari.
But do they still include the parts? Because from what I understood, even the parts you have to get them yourself.
Sorry, even the?
Even the parts you have to get them yourself and maybe put them in your distribution, because not everything is included in Cloudera.
No, but they try to give you a full view of everything that is in there. They want to, like especially Cloudera, they want to give you an enterprise solution to have all these components and have them work together. But the moment that you start drawing out of the box, then things become finicky. Especially, well, a whole while back, Cloudera was only focusing on batch, and they were not doing anything with real time. Back in the day, Storm was pretty popular, and I wanted to work with Storm. We had some valid cases to work with Storm, because we needed to do things in real time. And at that point, you find yourself in like, yeah, now I need to set up a separate system totally outside of this distribution. We paid a lot of money for this distribution, why can't we? And you get that kind of discussions. I haven't seen, but there probably are environments where they try to incorporate everything together, like and the scheduler, but the problem is that because you have the building blocks, you can decide how you can make them or how you can combine them into building a system that is specific for you. Because there's so many ways, it's like Lego blocks.
Sorry, then don't anyone have a solution, like say, let's take a metaphor, another example, WordPress, you have so many building blocks and things that you could add to your WordPress, and there are some kind of internal market and you could just add plugins. Basically, maybe Cloudera or anybody should do that. I don't know.
But that is Cloudera.
Okay.
Cloudera has a marketplace where you can say like, I want to work with Kafka. I click on Kafka and I can deploy Kafka in my environment. But the problem is that they're going to deploy Kafka for you, But what you will do with Kafka and how you will use it is totally up to you.
Yes, normal. You
That-
can do everything.
That's why, well, we can have a very long conversation about that one. But the thing is, that they will give you the components that you need to do something. But in the end, it's up to you to basically do it. Like if you look at, there was a slide, there was a big data landscape. Anybody has ever seen big data landscape?
900,
Yeah. So when I started, there were still empty spaces in there. Now, so every 2 years, there was a guy called Matt Turk who basically releases an overview of all the technologies that have to do with big data. When we started, we could all post them on one A4 page. Right now, we cannot even get them on a wall, I think. So the challenge for a data engineer, the challenge for a data architect is to understand which technologies to use in which situations. And sometimes when you're in an organization, you need to settle for something where they can have a service contract. Because you're dealing with managers, and at that point the scapegoat principle is in major effect. But keep in mind that you are the guys who basically need to build the pipelines. You are the guys who basically need to decide on how to take all these components together and build something that works. Does that answer your question, more or less?
Yeah.
Okay. So I want to take some time to talk about the team. Because in a lot of situations, in a lot of companies that I've been, the problem was not the technology. The problem was a team. Whether it was a group of people who have been doing a totally different job, and coming in, and now had to deal with big data, but did not possess the big data mindset. Or it was data scientists, operators, engineers who could not work together because they have different views on things. So when you look at a data team, these are basically the 4 core people or skills that you need. You need an architect. Your architect is the one who is going to provide you with an end goal and a path to get there. He's basically using those building blocks and say, like, this is how you're going to combine them. Your scientist, on the other hand, is someone who will look at data and discover new ways and new opportunities that are inside that data. He creates a blueprint of a factory on how to create insights out of the data that you have available. It's important to know that he creates a blueprint. You don't take a blueprint in production. Okay? Because it's up to your engineer to basically take that blueprint and convert it into a factory, into something that will generate these insights on a continuous basis. So not a one-off, not something that you just do once on data that on a file that was dumped from a system. No, I want to have this all the time. Because in the end, I want to integrate it back. I want to make those insights actionable. I need to do something with them. If I have to hire someone every time that I want to do something, it's going to be very, very costly. The last one, but certainly not the least one, is an operator. Because you need someone who makes sure that this factory keeps on running, who knows all the nitty-gritty bits about how you make something like this work, who knows distributed systems, someone you can go to when something goes wrong. There is a lot being said about data engineers versus data scientists. Because this is basically, when you go in any organization, or in a lot of organizations, they have a tendency to basically say, like, okay, we have a data engineering team and we have a data science team. Please Please, please, please don't do that. Data scientists are different from data engineers. Data scientists are programming because they have to. They write an application because they have to, but they are interested in the mathematics, they are interested in the algorithms, not in the programming. A data engineer is interested in the programming. And not only in the programming, he wants to build something that can sustain failure. He wants to build something that is robust. That is something totally different than what an engineer wants, than what a data scientist wants. So in a lot of organizations, you have these data scientists, and they're building models, they're building algorithms to train models. And once they have them, they throw them over the wall to the data engineers. Sounds nice, but the problem is that a data scientist is using a different language, probably, different concepts than your data engineer is doing. Which means, in a lot of cases, it means that your data engineer has to rewrite everything from scratch. Because your data scientist used toolkits that are not or do not scale. Data scientists like to use pandas and Python. I would like to use Python in production. I have no problem with that. But the fact is that a lot of organizations still want to use a Java system or want to have an engineered system with some robustness, with type safety, and they want to have that engineered. One other thing that's very important that a data engineer does and a data scientist often does not is to take into account what happens if data is wrong. What if you get data in that you cannot process? Well, a data scientist would say, like, I remove it because I cannot do anything with it. But a data engineer doesn't have that luxury because he needs to build a pipeline. He needs to build something that cannot go down. He cannot say, like, it failed, let's rerun it, because probably if he wants to rerun it, it's going to take ages to complete. So he needs to incorporate the logic, not only the logic of success, but also the logic of failure into his application, into his pipeline. Which means that he needs to detect when something goes wrong and basically fork that off to a different file, fork it off to a dead letter queue, fork that off away from the data that he actually wants to use. This is something that you do not often see with data scientists. Also, I still need to see the first data scientist that actually writes unit tests or testing. The biggest problem actually is that no single person can perform all these skills. When you look at an architect, you have engineers that are pretty good architects. You have engineers that are pretty good operators. You even have data scientists that are pretty good operators. But you do not have a data scientist that is a stellar data engineer or a data engineer that is a stellar data scientist. If you find them, please contact me on my email address because those are the people that I want. Everybody is looking for them. Everybody. Because for a long time, companies and salespeople were saying, like, ooh, data scientists, those are the people that you need in your organization. Which is true. You do need them. But what they fail to tell is that you also need those data engineers. This is one that surprises a lot of people. So basically, for every data scientist that you have, you need 3 data engineers. I've worked at a major bank, and there were more than 20 data scientists and 6 data engineers. I couldn't start to express or explain to you how much pressure there was on that team. Data engineering requires more time because of the reasons that I said. You can not only take the success scenarios in mind, you need to deal with all the failures as well. That's why it takes more time. If you want to build something robust, it takes time. No shortcuts can be taken there. So usually, I try to strive to a team of these kind of roles. I want to have one architect. I want to have one data scientist. I want to have 3 data engineers and have 1 operator. This sounds very simple. It's a team of 5 people, 6 people, sorry. Sounds plausible. But then usually management comes in and they tell you like, we found another 3 data engineers in a closet somewhere. Let's add them to your team. While it works for the data engineers, if they would say like, we have found 2 architects in a closet, that becomes a lot more difficult, sorry. What my suggestion is not to grow the team, but grow your number of teams so you can do or start doing things in parallel. Yes, you need to synchronize. So your architects need to talk to each other, your engineers need to talk to each other, and your scientists and your operators as well. But it's much more feasible, it's much better to have 2 teams and 2 smaller teams than 1 big team that you have to coordinate. Who's up for a break? Okay, let's take 5 minutes. Start again. Let's talk about implementation. The moment that you actually decide, like, okay, I know what building blocks I'm going to use, and I have a vision of what I want to build and what I want to create. Let's get to that stage where you can actually where you're actually going to make your hands dirty. You can start playing with it. One advice that I give everyone is make small steps. Dolphins, not whales. With whales, I mean the animal and not, whales make very big jumps. Dolphins make very small jumps, incrementally. Be a dolphin, not a whale. It's going to help you to incrementally provide and prove that things work. The first projects that we did when we start with big data were whale projects, big projects, because they heard like there is this new thing about big data. There were even some cases where some CEO of an organization came to us and said like, I got 3 million euros for doing something with big data. What are we going to do? I was like, meh. My suggestion of just giving it to me and me starting a startup wasn't that enthusiastically received. Anyway, the first thing that you need to do if you start implementing is that you understand what you need to do. Usually you will get a case, usually you will get a request. But you need to understand what they expect. How is that case going to generate business value? And what does it actually mean to be successful? I mean, in the concept of the case. In real life, whole books are written about that. You need to understand the scope. You need to know what is in scope and what is out scope. This is not something new. These are engineering practices, developer practices. If you do any project, you need to understand what you're going to do and how it contributes to your business. But also understand what your assets are. What data do you have? What data don't you have, but would you really like to have? In the beginning, when we were doing projects, everybody was like, oh yeah, then we can look in people's social profiles. And we can mine them and we can analyze what they do and then we get a full view of this individual. That was pretty funny. Because one of the first things that Facebook or Twitter or any of the other ones did was hammering down their feeds and their APIs and not allowing you to do anything anymore with that data. And then it became difficult. Because you need to be original when it came to coming up with ways of using data. But it's actually not that difficult. There are data sets out there. Things like traffic, things like weather. Go to open data initiatives. Ask Ton if you like. He knows all of them by heart probably. There is data out there. Use it. And you don't necessarily have to pay for it. Also know which technologies you have. What you can actually use. Are there certain technologies that you cannot go around? If an organization has made an investment in Cloudera, chances are that you will have to use Cloudera. Also understand what skills you have in your team. And more importantly, understand what skills you don't have in your team. Because then it's up to you to either decide to hire them in or to find them. Understand if they are required to make this story a success. The next step is probably one of the shortest steps. Sketch it out. And I don't mean like creating diagrams and putting a lot of time in making these nice visual things. Please don't. Just take a white paper, take a whiteboard, take a marker and start sketching. Sketch things out, remove it, start again. That's it. That's the process that you need, because that will generate focus. That will show you what the important things are, what the difficult things are that you have to accomplish. And these difficult things are the things that you need to validate first. It's important when you do sketching that you start from your goals and you work towards your assets, not the other way around. If you start from the assets and you work your way up to your goal, you will probably end somewhere where it doesn't need to be, or you don't need to be. If someone asks you to give you a view of a customer, starting to look at all the data you have of that customer is probably not the right thing to do. You should ask him, what kind of information do you need? And start from there. Then the first step, the first thing that you do is you make it work. This sounds very simple because it is. It's hacking things together. And hacking in a positive way. It means that you're going to prove it works. You're going to prove that those difficult things that you identified during sketching, you can actually solve those. And you can also prove that it provides value. It provides real business value if we do this thing. Because you will need this in order to convince the rest of business. It's important to get to the essence and stick with it. It's so easy to start wandering off and implementing this really, really cool feature because you can, but really nobody's interested. It's too early. Just make sure that you can prove that something works. Do the minimal work to prove that. Really the minimal work. Once you get a feel of what actually works, sketch. It will help you. Really, it will help you. The second step is, once you have proven that it works, because if you have proven it doesn't work, then you just stop, right? But if you have proven that it works, it's up to you to make it beautiful. But what does that mean, making it beautiful? It means that you're going to make it technically beautiful. You're going to write tests, unit tests, in order to prove that it keeps on working. You're going to document your code. You're going to strive for elegance in the solution that you have built, which means that you're going to use design patterns. Design patterns are ways that problems have been solved in programming languages. There are books out there that explain all these design patterns to you. These are like blueprints how you should solve a problem. It's really cool if you have those in your application. It makes difficult things simple. One thing that you might want to do, but you don't have to do, is to generalize and to make certain components generic and reusable. Because it could very well be that your next project can benefit from some of the things that you have been building. One thing that is often done in the beginning of a project is to look at what is the most efficient way to make this, and efficient in a technical way, not efficient in a way that we should build it, but can we make it perform like really, really well? Do not optimize in the beginning. We're going to spend a lot of time without actually having figures to optimize with. If you want to do optimization, you need facts. You need to know what your baseline is in order to optimize, because otherwise you're optimizing and you don't know what your goal is. So make sure that you have something, that you have that baseline, that you have those base metrics, those base facts, then you can start performance optimizing or optimizing the application that you've written. Do load tests. This is an important one with data. There are tools out there that can generate data, and that can generate data with specific patterns. That is important. It really is. I can build a system, provision it anyway, but if I do not take into account what kind of data I'm getting in, it could very well be that I've created bottlenecks that I've not known of, or that I did not anticipate. One thing that is far too often overlooked is making something maintainable. You have a lot of engineers that really like to engineer. You have a lot of scientists who really like to do science. You have a lot of architects who really like to architect stuff, and they make very complex systems. But the problem is that the more complex a system is, the harder it is to maintain and operate it. So make this something that you validate your solution against. Make sure that you build simple solutions. Make it as simple as possible, but not simpler. Make sure that you have monitoring, that you know if something goes wrong on a technical level, on a functional level. Make sure you have alerts in your system. As I said, this is something that we do all the time now, to make sure that if something goes wrong, we get notified and we can dive in an environment to investigate what actually went wrong. This often means going into the log files and trying to see, like, okay, this event happened over there, this event happened over there, time is more or less the same. Are these correlated to each other? You need an environment to do these kind of things. You can either buy an environment to do that, or you can use one that is already available. These few steps that I've explained, we basically do for every feature that we build. Starting from making it work, going to making it beautiful, going to making it fast, going to making it maintainable. And again, every time again. This is how we provide features, but we keep it small.
To do all this, we also need an infrastructure.
Sorry?
To do all these things, like we also need an infrastructure where we have to work on, right?
Yeah.
The servers or whatever, the small, either small ones or the big ones.
Mm-hmm.
So even in the infrastructure also we need to start with very less investment.
Yeah.
And then to scale up.
But you can. And the thing is that if you have an operator in your team, you basically have all the support you need to build the thing that you need to build. There aren't that many, like, okay, yes, you need to set up a base environment.
And setting up of a cluster with some very few needs,
Mhm.
few nodes, but also if you have to scale up, you also need to do same amount of work in setting up all the nodes in the cluster, something like that.
Yeah. But you have,
Big work.
in our case, what we saw is that in a lot of situations, either you go to the cloud to do your stuff, but if you want to do it on premise, that means that you need an infrastructure guy as well. Which means that apart from the operator that you have, you will also need someone who is busy with doing the core infrastructure stuff. In some cases, that can be the operator. We have had teams where basically the operator was doing that as well. The problem is that once your platform becomes more and more successful, once your initiative becomes more successful, you need to start to collaborate a lot more with other teams that are providing value, that also have this infrastructure person. So the more that you grow, the more that you need to start communicating with each other, and that's where usually things go wrong.
And to perform the tests before putting something in production,
Mm-hmm.
you suggest to have different environments in the same cluster or different clusters?
Different clusters.
Then in that case, again, the small things like the infrastructure, setting up some ecosystems, like even a small configuration difference between the two clusters, we are not sure until we start doing the first thing.
Yes and no. What we do right now is we script everything. We use Terraform, for example, to say like this is how we want our cluster to set up. Do we want a test cluster? We run the script and we have a test cluster. This is the thing that we can do because we're running in the cloud. If you're running on premise, of course things are a bit more difficult, but even then you can do similar things.
Maybe some tests also, the small tests perform the same thing, but again with use data again they may.
So what you usually see is that your production cluster and your acceptance cluster is of the same size and of the same kind of nodes.
Not exactly the same, but yeah, you have two different clusters.
If it's not the same, you cannot do the correct tests.
Yeah.
You're basically testing something.
But they have the same Afterworks version, ecosystems, everything are the same. But
Yeah, but it doesn't matter because your data is going to be distributed in a different way on one cluster than it's distributed on the other cluster, which means that sometimes things will become or go wrong. We have seen things where we had behavior on production that we did not have in our acceptance environment. And we couldn't even replicate that behavior because that's something to do with a certain amount of nodes and a partitioning key that was giving problems. So only in that situation we got into issues. And these are the hard ones to debug. These are the issues that take time to solve. And if something like that happens in production, I can assure you that people are in your neck breathing to get that solved. So in the past I've been hesitant to say like if you want to do something with big data, go to the cloud, because a lot of people basically are afraid of it. But if you look at the flexibility, I don't see a problem with having my test environment and my development environment in the cloud. If I want to run on-premise, please do so, run on-prem. But at least give yourself the flexibility of doing things in a cloud environment. It allows you to scale things up, it allows you to execute things very easily, and especially with scripts today, with things like Ansible or Terraform. Spawning a cluster is just a script, it's a command line, it's one thing that we need to type in a console, that's it. And we have a new cluster and we can start working. So make sure that you have that flexibility. Even if you do things on-prem, make sure that you scripted everything. That if something happens, if someone screws up the whole environment, you can basically run a script and your whole environment is there again, including the data. Make sure that you put time in that because that is valuable. It really is. It saved my ass many times.
Regarding the security of the clusters, I mean accessing the clusters itself,
Mm-hmm.
something like Cadburyized clusters and
Yeah.
uncategorized. So those things affects the performance of the cluster also?
Yeah. I mean, any kind of encryption, any kind of token exchange that you add to your cluster will have an impact because it's something extra that you need to do every time. You need to validate every time whether you're allowed to do something or not. In some cases, they take shortcuts, but it has impact. It certainly has impact. That's why you see in a lot of situations where basically even the big data environment is not Kerberized. Because they say like, okay, we make sure that we put it behind a firewall and we make sure that nobody can actually access the big data environment. If they want to do something, they have to come through one gateway, one jump node or whatever.
I think we have both behind the firewall and Cadburyized.
Yeah. The thing is, I remember spending a lot of time in getting a big data cluster secured because you have basically everything is talking with everything, which makes it very hard to secure it. And even then, you can secure access to it, but if you want to start working with ACLs and allowing on a data level, saying like this is allowed and this is not allowed, and even on a record level, saying like on this record you can see this email address, but on the next record you can't, that is a challenging part. That's where it becomes really, really difficult. I haven't seen any solutions that do that in a good way and in a maintainable way. You don't want to put 15 people full-time and just managing all the rules and all the exceptions, because at that point it's not a maintainable system anymore. Did that more or less answer your question? Okay. So, I talked about all these components and everything that you can use to build a platform. But if you go to an organization and you need to start from scratch, it could very well be that you end up with something like this. This is something that I just sketched. It's not a full-blown architecture. They're missing a lot of components. But what I wanted to show is how real-time or streaming is working together with batch and is incorporated back into the environment. Over here, you have data sources in your external or in your organization, a database, a set of files, it doesn't matter what, right? You can take these in, you can read these in your streaming environment and in your batch environment. In a lot of situations, we actually see that they are being read in the real-time environment, in your streaming environment, and then in one of the handlers, it's being written to your batch environment. Because yes, you can do batch with streaming, you can not do streaming with batch. I can read a file, split it apart, and every record, and deal with every record. I can still reconstruct the whole file. Let's focus on batch first. You have your data, you're going to store it somewhere. In the cloud, S3, on-premise, usually AGFS, or something similar. You will have jobs that will take that data and do something with it, transform it. You will actually have multiple jobs scheduled behind each other or in sequence of each other. It could very well be that this job is basically generating a data set that's used by this job, that's used by this job, and that generates a new data set that I want to make available. But I could also have a job that takes data from storage, prepares it, and in the end generates a model, a machine learning model. Because in order to train a machine learning model, I need a lot of data. Yes, you can train algorithms or you can train models in real time, but it's non-trivial, and right now I have only seen it in 2 occasions. This is something that you see much more. You actually use your batch environment to come up with static reports, data sets that you want to exchange or drop back into an existing system, or machine learning models that you have trained. Because once you have those, especially the machine learning models, you can re-inject them in your real-time flow to be evaluated. I use my whole history of data to train my model. Once I have my model, I put it in the line of fire. I put it to be executed every time a new event is being pulled through. When you look at ingestion on a streaming level, you will need to get data in somewhere. Use Kafka Connect, for example. You will read it from somewhere, preferably a streaming source. It's always fun to read from a stream and not having to parse a file and split it out into events and then pass it through. Feels like cheating. You read these events, and every event is being shot through what is called a topology. Topology is a combination of processes, of processing steps, and ways to connect these processing steps. You can do joins. You can do splits based on conditions in the data. These splits we will use very often to test for failures. But you can figure out a way how to combine these processing steps into a flow, into a sequence of processing steps to end up with a result. It could very well be that you have one thing sitting here, one processing job sitting here that needs that model that we trained in order to make a prediction. Does he have diabetes or not? Based on the data that we get in. Are we going to allow him the insurance or not? Based on the data that we get in real time. But actually, before we can ask the model these questions, we need to prepare the data. And we need to prepare the data in real time. That's why you have all these steps before. Most of the times, even when you have the result, like, yes, he has diabetes, or no, we cannot give him the insurance, you will still have some post-processing to do, some enrichments to do on that result before you send it back into the organization over here. There are occasions where you don't shoot something back into the organization. There are moments where you just want to send a notification from this, or do an API call, or contact a service provider, send something out. When we talk about things being data-driven, then we talk about the fact that you can actually build a system that interacts, quite vividly by the way, that interacts with your organization, that interacts with your processes. And they are basically the trigger to do other things. Being data-driven, the fact that you get a notification, and that notification starts a whole process of investigating and doing your stuff, that is data-driven. Is there anyone who has a question about this? Okay. On to the advice. It's finally done.
One question from the previous slide. That would represent the processing part.
Yeah.
And then after what do you have the integration step?
The integration part, so what you usually have is you have these topics in real time. You have these streams of information. So what you will do if you want to integrate it back into your organization is that you're going to put a listener on there for all the events that come through. You're going to take them together and then update the database, for example, that is already in your organization. Or you're going to trigger a notification every time that an event comes in. Or you can even put some criteria over here and saying, like, every time that I do my model evaluation, it will give back a score like 80% certain. If it's lower than 60%, we don't do anything with it. If it's higher than 60%, we send it to there. And if it's higher than 90%, we send it to somewhere else. That's the kind of thing that you can do in there. The fact that you have things in streams makes it possible for others to integrate with it. either to put it in their own data systems or use the stream directly to build new features or new applications or new services. Okay? So let me get to some advice, some things that I've learned. First of all, architect for change. Make sure that if you build something that is flexible, make sure that you can take one technology out and replace it with something else. Think in concepts. Think in these building blocks that we talked about. Because once you think in these building blocks, it allows you to basically say like, okay, maybe in this situation we can use something totally different, or we need to use something totally different than we did before. Or we get into issues with the technology, the processing technology that we're using. Maybe we need to use something different. Make sure that your system can cope with that, and you need to write the minimal amount of code to make that change. One very important thing is that you have to create an environment for data scientists to play in. That means that you need to be able to take your data away and give them a sandbox where they can experiment with their tools, not with what you give them. This is something that is very, very, very difficult in highly regulated environments. Obviously, because the data is so sensitive. Make sure that you create an environment where your engineers can make mistakes. How can you expect from your engineer to build the perfect program from the start? I've never met someone who doesn't write bugs. Ever. I've had a lot of beers because someone claimed he didn't write bugs, but you need to give them an environment where they can make mistakes, where they can screw things up, and screw things up good. I mean, making a cluster unavailable, good. Once you get onto a point, or at a certain point, make sure that you take your time and be patient and explain not how you will do something, but why you do something. Especially if you come across to people who have been in the data business for a very long time. They will tell you like, this is not new. We have been doing this for the past 10 years, 20 years maybe. Explain them that's more about thinking different than the technologies themselves. Finally, my favorite one. People who put proof of concepts in production deserve a high five. In their face, with a chair. I strongly believe this. Don't ever, ever make the mistake of hacking something together and putting it in production. It will bite you in the ass, especially when you're dealing with data. It's so easy to stop when you made it work and not to make it beautiful or fast or maintainable. But know that it will come back and haunt you, I can assure you. Any questions? Nope. If for some reason you're lying awake at night and thinking about this and you don't get an answer or you don't come to a conclusion, you can always send me a tweet, always send me a mail, ask me why or how or whatever. I really like to see more people being inspired by using data in the good way. Thank you.